Okay, you've got all the tools. Let's put it together and get down to it. You know, when you learn an introduction to something, usually you learn how to do it without the specifics, the details. What's the detailed meaning? So we're doing that with vectors. We're just getting used to them a little bit, and then we're going to be using them and using them and using them. So you'll get used to it. So don't overthink it too much, but we'll see some examples. This is vector 6. What we need to do is add and subtract vectors, any vectors. So I can add displacement to displacement, velocity to velocity. I can't add velocity and displacement. I can't add those two because that's adding meters to meter per second, or miles to miles per hour, or any mix like that. So I can't do that. But any one type of vector, like a velocity vector, can be added to another velocity vector. A force can be added to a force. Okay? All right. So we're going to add and subtract. Now we're not going to multiply vectors now. We'll multiply vectors in two different ways later. If you're taking a math course and you need to look at that, you can look at my videos 7M and playlist 7N. Okay, but if not, hold off because it'll be a little too much. So this is good news. It's easy. Vector variables. If you want to add and subtract them, you just get to move them around without any details. So I just made up some equation. I have no idea what it means, but vector A, B, C, and D better have the same units. They better be talking about the same thing. So let me go over here and let me solve for something. I don't know. Let's solve for B. Well, B is equal to pi vector C, which has magnitude and direction, minus 8 times D. I had to subtract minus A. And let me just keep the half over here. And then multiply across by 2. So if I do that, I can get the 2 here, and I can multiply 2 times that is 16, and then a 2, and what is that? I don't know, but I can move it around. You can add and subtract. Okay. I could solve for C. C, vector C is equal to, well, let's see, I can move this over here. Now it gets to be, if you're too clever and too tricky, you're going to make a mistake. So I could say A plus 1/2 B plus 8D is equal to pi C. And then I would write another step, with the magic of dry erase, I can divide by pi, which is just a number. It's about 3, right? Divide by pi and divide by pi. And that's what C is. What is it? I don't know. I need to get specific. So we'll get specific. But the beauty is I can set up a relationship and then move it around to solve for what I want. And then I go, well, I better find out what 1 over pi times A is plus 1 over 2 pi times B. And so how do we do that? Well, one way to do it is by arrows. Nothing more to vector variables than that. Just move them around. Don't overthink it. But you set it up based on whatever you're dealing with. When it comes to arrows, we call this graphical addition and subtraction of vectors. Now you can do this to scale. You can use rulers and protractors and draw it carefully. There's going to be some uncertainty built in there, right? And you could do it that way. But usually what we draw is a rough sketch, and that's going to guide our calculation. It's very important, otherwise your calculations can drop a plus or minus sign, pretty quickly. Remember to keep your units though, right? So what's the method? Tail to tip. In the past, people used to call it head to tail. That was not really a good description. It's really tail to tip. And here's the steps. You can add or subtract any number of vectors at once. One to another one, to another one, to another one, to another one. And then in the end, you've got the sum of those vectors. So it doesn't matter the order, just like doing the algebra. It doesn't matter which order you put it. But you can take any vector as the first vector and sketch it, again, roughly or to scale. When you're doing it roughly, you know, if it's more, then make it a little longer. And if you can kind of scale it by eyeball, that helps. Anyway, sketch one, anywhere, doesn't matter where you put it. Then take the tail of the second vector, any of them that you're adding up, just grab one, put the tail of that next one to the tip of the first one. So first you draw this, it's got a tail to tip. Then you take the tail of the second one and put it at the tip, tail to tip. And you repeat, putting the tail of the next vector at the tip of the previous vector. And you'll see what those words mean in a moment. When you're done, we have what's called the resultant vector, or the net vector, or the total vector, whatever you want. The answer that we're looking for. I recommend drawing components as dashed lines, and I recommend drawing the resultant as a double line arrow. It's just visually you're less likely to make mistakes. How do you draw it? You draw it from, that is the resultant tail, is from the tail of the first one, which is the beginning, right? The beginning of your sequence. The resultant tail starts at the beginning, the tail of the first one, and ends, the resultant tip, at the tip of the last vector. Okay, so if you think of your drawing, you started at the tail of the first one, then you went up, and you went up, and you went up, and you went up, and you ended at the tip of the last vector. And where did you started here, and you end here, so the resultant goes from beginning to end. Let's see that. And then you can see it, you can calculate it, or you can measure it, and you can get the net amount of the resultant, the angle, the components. It's just right there. It's just you're going to break it down into triangles. Okay, so let's take a look over here at some examples. Give this a shot. And I've drawn three vectors here. Of course, I can put my coordinate system any which way. Just for the sake of doing this, I might as well kind of go plus and plus. I'll call that y and call that x. You can call it whatever you want as long as you're consistent. I could take any of these vectors and start with it. Okay? And you should prove to yourself that a plus b plus c vectorially or graphically is going to give you a resultant vector with the same length and direction as c plus a plus b, or so on. Now I have something up here. These two I put an arrow on, here I did not. You want to be consistent. Now this is vector b, so I can do that, that's fine. Later on, though, you'll see why I like to put the magnitude, just b without the arrow, next to the direction. But fine. What do I want? Let's just do, I want a plus b plus c in any order. That's equal to b plus c plus a plus whatever. So how do I do it? Well, I just draw one. And if I'm being careful, then, be a little bit careful. Don't be too sloppy. So I know, okay, there's a. It's going to go some over that way and some over that way. So I need to draw kind of that angle. I could start with A. All right, let's do that. Let's start with A. I'm going to try to reproduce that and measure it. I got about that far. I'm going to find A is something like this, right? So there's my first vector. A. And then I've got, I don't know, C. Let me do C. Who cares? So there's A. Notice I started there. That's the tail of the first vector. Now I'm going to do C, just because. And I got it kind of, I got this direction here, so maybe I got an angle here and the complementary angle there. So I'm going to draw my coordinates right at the tip. This is something that confuses people. So I've got the coordinates here. I can put the coordinates there. It's just graph paper, it's a grid. And I can make C go, if this was, for instance, 20 degrees, then the 20 degrees would not be from the previous, it would not be from A. It would be relative to your coordinate system. So people mess that up quite a bit. So somewhere in there, and that's like, okay, kind of like that. This is sketch, so I'm not going to worry too much, but I want it somewhat good. All right, great. There's C. So that's A plus C. And if that's all I wanted, I would be done. What I've done is place the tail of the next vector to the tip of the previous vector. The result then would be from the tail of the first, from the beginning, to the tip of the last. And then that would be my resultant. And it would be going some to the right and some up. But wait a minute, I got B. Okay, fine. Let's make it, we can do as many as we want. So let me draw B in there. It's going to be down. Let's see, I got my coordinate system here. So I've measured the angle. Either of these angles is fine. I would put a coordinate system right at the tip of where I'm starting. And I'd measure that angle from that coordinate system, not from C. That's a huge mistake. Yeah, it's a little angle, and I go out here. How's that look? Something like that? No, not perfect. It's a sketch. So something like that. Yeah, all right, good. Cool. So now I've got A plus B, A plus C plus B. And where's the resultant? Well, it's from the beginning, here, to the end, here. And again, I recommend double line. Boom. What is that? That's A plus C plus B, which is equal to A plus B plus C, however you do it. So now, I could redo this thing. Let's see if I don't want to get too slick, but you should try it. What if I did A, and I put B at the end of A? Put B over here, it would come down here. It would move right around, I don't know, here. A little bit longer than that, a little bit longer than that, something in there. And then I'm going to add C. So now I'm going to do it in a different order. A plus B, and now add C. So I slide C over, make a coordinate system. It's going to go a little bit over here. And sure, I'm cheating because I know where I want to end up. So no matter which way I go, A, then B, then C, or A, then C, then B, I get the same resultant, the same result. And then I can say, hey, that's my answer. It has components some amount this way, and some amount that way. If I call that D, this would be dx, and this would be dy, and D would be the result. Whatever they mean, right? You could do this with velocities, if they're all velocities, forces, if they're all forces, displacements, if they're all displacements, whatever you've got. Okay, so hopefully that makes some sense. We can do one, then the other. So let's move on from there and just do practice. So it's kind of hard because you're just sliding these arrows around and you're losing track of the physics or the physical process. But you get to do that. It is tight. And you can just move one, then the other. Okay, I got another one for you after this, but let's talk here. What about subtracting a vector? Well, subtracting a vector is adding the negative of the vector. For example, A minus B is the same as A plus negative B. Well, what's negative B? And the answer is simple. Any negative vector is that vector flipped. So if it's this way, it's that way. If it's up and to the right, then it flips down and to the left. It's the flipped. If my vector is in the negative direction, then the negative vector is in the positive direction. Or whatever. And check it out. If you write this, let me just as an example, here's V1, and it's a velocity. and it happens to be in the negative x direction, the positive y direction. I've sketched the components, negative x direction, positive y. So then I've got v1, the components are dashed, the velocity actually is there, whatever, v1, that's the speed, that's the direction, it's happening right here, right, I'm not moving there, that's where I'm directed at that moment. What's negative v1? Well, negative v1 is, you can just multiply the negative across. That makes that positive 2.0, oops, stuck with two sig figs. So that means it would be going here. I flip the x component. And the negative sign flips that sign, so negative 7.0 meters per second j hat, which means I go down. And the result, if I draw it correctly and measured it and everything, is this way. So this is the vector negative v1, and this is the vector v1. And what you've done is you flip the x components and you flip the y. By the way, did you notice that the graphical addition is just like the components? This component vector plus this component gives the total. So that's all the negative is. So if you're going to subtract a vector, first flip it, then just add it like you did before, graphically, or we're going to see by components. But the other thing is that any number times a vector just changes the amount or the magnitude of the vector. It doesn't change the direction. How do we know this? Well, A and A are going in the same direction. So say their displacement. If I displace 2 meters this way and I displace another 2 meters this way, then that's 4 meters. So I'm just doubling the length, or 3/4 the length, or 1/2, or pi, or 3 pi over 4, or whatever you want. And so multiplying that just changes the length because it's equivalent to adding that vector over and over. Or if it's half, then it's equivalent to taking half the length. Okay, so now the last little bit that I wanted to show you. So just relax and realize that, that's fine. Keep your units. I want to go back over here and give you one important example. It's one that's messed up quite often. I'm going to stick with my standard XY coordinates for now. And I'm going to put my origin there. Okay, and I'm going to start, doesn't matter, any quadrant, I'm going to start somewhere here. So that's state 1, moment 1 in time. My position vector then is R1. I'll write that as a vector to emphasize this. It's okay either way, right? And then I'm going to move along some path and end up over here. State 2. So this is R2. And my question for you is, where's the displacement from 1 to 2? How do I draw displacement d 1 to 2? Well, wait a minute. That's another way to write that is delta r, change in position from 1 to 2. Wait a minute. That's just how far in what direction from 1 straight to 2. I don't care what path you took. The displacement's just start to finish. So then the answer should just be this, right? I'm going to draw it as a double. How would I get that? I mean, that seems right. How would I get that? Oh, wait a minute. This is equal to the change, so that's going to be R later minus R earlier. So I'm throwing this stuff around, and that's all you got to do. Any applications. Oh, wait a minute. That's R2 plus R1 flipped. Now, if I took R1, I don't know if you can see that very well. If I took R1 and it was heading this way, let me grab something, excuse me. Grab this guy here. A little astronomy prop. There it is. And I slid it. If I wanted to do R2 plus R1, I'd go R2 plus R1. Just put it parallel, and then the result would be here. But that's wrong. It's R2 plus negative R1. And you say, hey, isn't that wrong? Let's check it out. I can get my hand around it. Make it parallel. Up here. About the same length. That's pretty good. This is R2, and this is negative R1, right? R1 flipped. So R2 plus negative R1 is in the exact same direction and the same length as this. You say, wait a minute, but it's over here. No. Displacement, I don't care where I am. It doesn't tell me my position. If I put my coordinate system here, I'd find that that angle was the same as that angle. So they're moving, or the displacement, the change is the same amount in the same direction. You know, that one you might have to think about for a while. But this is how you do displacement. First off, it's kind of easy to draw. It's from the starting place to the ending place, independent of how you got there. Fine. But you need to be able to work the algebra a little bit. You might say, well, why do I need this? Because we use it later. Displacements, change in position is the later position minus the earlier position. That's the later position plus the earlier position flipped, the vector. And you do this. So you might run into a little bit, maybe not. It's a nice little example, and not too bad. Okay, so the next thing that we need to do is to add and subtract vectors by components. And we're going to divide and conquer. Now, we're still going to want to just get a sketch, but we're going to break each of these into components. Okay, and so what I'm going to do there is to say, well, R2 is going this amount in the x direction. Negative R1 is going that amount in the r direction. So that, with this, add it or subtract however you want to, gives what? In the x direction, it gives that. That gives the result in the x direction. So the x component of R1 plus the x component, the x component of R2 plus the x component of negative R1 is going to give me the result. And I can do that also with the y direction. R2, this guy, goes up that much. And negative R1 dashed goes up that much. So this blue plus the red gives me this plus that. Hey, the sum of the y components gives the y component of the result. And the sum of the x components gives the x component of the result, taking care to notice the plus or minus signs. And that's what we're going to do. We're going to divide and conquer. Break every vector up into its x components, and then add those up, pluses and minuses. Break every vector up into its y components. Add those up, pluses and minuses. Then I get the result. I get the result x component, the result y. You want the magnitude? Fine. That squared plus that squared